Welcome back to mass transfer operation 2 course, and in the last class we discussed the details about the continuous dryer. In this class we will be discussing the drying time calculation from drying rate curve. So, before going into the drying time calculation, we need to discuss this one, the important topic like the movement of moisture within the solid. So, the first movement is like liquid diffusion, that due to the concentration gradient between depths and the surface falling rate period, the liquid diffusion takes place. And the another movement is capillary movement, that unbound moisture in granular and porous solids moves through the capillaries, then this is due to this surface tension only. And constant drying rate period, as drying proceeds, at first the moisture moves by capillary to the surface rapidly enough to maintain a uniformly weighted surface, and drying rate is constant. So, that is we can say this one just by we can say the capillary action, the water moves from the interior of the wet solid to the top surface of the wet solid. And another one is this vapor diffusion. If heat is supplied to one surface of a solid while this one drying proceeds from the another, like in a tray, suppose we are supplying the heat from the bottom and the drying is taking place from the top of this one, then moisture may be evaporated beneath the surface and diffuse outward as the vapor. These are the we can say movement of the moisture within the solid. And calculation of drying time, like a constant drying condition, we have already discussed this one, still we are recapitulating those, like this flux is equal to say minus S s by A into dx dt, where x I is the initial moisture content, and say we can say this one x f is the final moisture content. Then whenever integrating this equation from 0 to t with respect to this minus S s by A dx by n, we will be getting this t in terms of we can say S s by A, and this one in terms of this n, and drying time remains constant at n c till x c, this one from x I, like this. From x I means they say we will start from here, and x c is we can say this one when constant drying rate stops. Now, we will be discussing about the constant rate period time. The T c is equal to S s by A n c into x I minus x c, and for falling rate period we can say this one, there may be two falling rate periods, like first falling rate period, then second falling rate period, like this. Say we can say this one the maybe first falling rate period may be we can say drying rate is proportional to moisture content. Then this first falling rate period, this T f will be like this, S s by A into x c minus x f by n c minus n f into ln n c by n f. So, that will be we can say this one time for the first falling rate period, or if the falling rate period is square of this we can say this one moisture content, then will be it will be like this T f will be S s by A into n c into x c square into 1 by x f minus 1 by x c. Then we can say the total time for this drying will be like T constant rate period and T final rate period, that is we can say this one T f. So, that will be S s by A n c into x I minus x c plus S s by A n c into x c square into 1 by x f minus 1 by x c. So, these are the we can say this one regular cases. Now, we will be discussing one case where the two drying rate this one falling rate periods are there, with the first falling rate will be proportional to x and second falling rate will be proportional to x square. So, the problem is like that, a wet solid having 32% moisture, that is on dry basis, is to be dried on a tray dryer to a final moisture of 1%. So, this is the requirement of the system, like final moisture content will be 1%. The solid loading is 30 kg dry solid per meter square area, that is we can say SS by A is equal to 30 kg per meter square. There are two critical moisture values, that is XC1 that is equal to 0.183 and XC2 is equal to 0.097. A laboratory test gives a drying rate of 4 kg per meter square hour. In the first falling rate period, the drying rate is linear in the moisture content. In the second falling rate, the drying flux varies as the square of the moisture. The equilibrium moisture is negligible, means we can say this one x star is equal to 0. We need to calculate the drying time. If the drying conditions are the same as in the laboratory test, so we need to mention any assumption if we have made. Okay. So, we will be doing this one step by step calculation, but here we will be doing one thing, that say the falling rate period here are two different falling rate periods, like the first falling rate period will be following this linearity and second falling rate period will be proportional to x square. So, let us start the solving the problem like this. We can say we will be writing this one, this LS by A, that is we have this one 30 kg per meter square, and Xi that is given as 0.32 and Xf that is given as 0.01 and Xc1 that is 0.183, these are all given, and Xc2 is equal to 0.097 and Nc that is also supplied, that is 4, that is kg per meter square hour. So, these are all given in the problem itself. Now, we need to get the correlations among all these x values along with the flux values, or we can say the drying rate values, like this n is equal to, we can say this one Nc, when we can say x is greater than equal to Xc1. Then first falling rate period, we can say this one first falling rate period. So, we have this NF1 that is equal to, we can say this is linearly proportional to the x values. So, we can say is equal to say A1 into x plus A2. So, this x1 that is given as 0.32. So, xc1 that is given as a 0.183. Say xc2 is given as 0.097. So, somewhere this xf actually is given as 0.01 and this x star is equal to 0. This is equal to 0, it is given in the problem. Okay. For second falling rate period, NF2 is equal to, say we can say beta into x square. So, for fast falling rate period, it is mentioned that for this case, say we have say Xc1 that is greater than equal to x greater than equal to Xc2. But for second falling rate period, we have this Xc2 greater than equal to x greater than equal to 0. So, these are the conditions these are given. So, we will be mentioning like the conditions like this. At x is equal to Xc1, we have this A1 Xc1 plus A2, that is equal to NF1 and that is also equal to NC, because that is we can say this one here, it is it is the, we can say this one at the beginning. So, we can say that it is nothing but NC, and at x is equal to, we can say at x is equal to XC2, where we can say this one XC2, I will take this one as XC2, say A1 into XC2 plus A2 is equal to NC2. Again, at x is equal to this, in this again at x is equal to XC2, here also we can say we have this NC2, that is a square of this moisture content, that then we can say this one is equal to beta into XC2 square. So, we have this one and we need to assume this one, that continuity, this one we assume the continuity of dx dt. So, at x is equal to XC2, like this one, that is XC2, that is XC2, that is XC1, that is Xi, then somewhere it is Xf, that is x star equal to 0. Okay. So, then we can say this one dx into NF1 is equal to d dx of NF2 at x is equal to Xc2. So, from there we will be getting like this, A1 is equal to 2 into beta into Xc2, and A1 into Xc2 from the above equation plus A2 is equal to, we can say this one beta into Xc2 square, or A1 will be equal to 2 NC, just from the above equations will be, just by manipulation we will be getting 2 Xc1 minus Xc2, and A2 will be equal to minus NC into Xc2 divided by 2 Xc1 minus Xc2, and beta will be equal to NC divided by Xc2 into 2 Xc1 minus Xc2. So, now we have this A1, A2 and beta. So, we have all these three values. Now, we need to calculate the drying time for different periods. Like this, we will start with constant rate period. So, drying time calculation for constant rate period, that is very easy to calculate constant rate period. So, for this period we can say from xi to xc1. So, xc1 from xi to xc1 for drying time calculation, like this Tc will be, Tc is equal to say Ss by A Nc into xi minus xc1. So, that will be like this, Ss by A we know this one, this is 30 and xi is equal to 0.32 and xc1 is equal to 0.183 divided by Nc is equal to 4. So, it will be coming as in terms of hour, that is 1.027 hour. So, this is we have got obtained as Tc is equal to 1.027 hour. Now, we have two falling rate periods. So, for first falling rate period, Tf1, that is equal to SS by A into integration XC2 to XC1 dx by n, though we have this one the minus SS by A into integration XC1 to XC2, but to make this positive we have changed the limits. That will be nothing but we can say is equal to SS by A into XC2 to XC1 dx by A1 x plus A2. So, from there we will be getting that is equal to SS by A into 1 by A1 into ln A1 XC1 plus A2 divided by A1 XC2 plus A2. Just by manipulating this A1 value and A2 value in this equation, we will be getting this say the final form of this TF1 will be like this. So, TF1 will be is equal to, just by putting this A1 A2 values in this equation, we have this SS by A into 2 XC1 minus XC2 divided by 2 NC into ln 2 XC1 minus XC2 divided by 2 XC2, and all the values are now known to us. We will be putting this value to get the fast falling rate time. So, it is SS by A is equal to 30, then XC1 is say that is 2 XC1 2 into 0.183 minus XC2 is 0.097 divided by 2 into NC is equal to 4 into ln 2 into 0.183 minus XC2 is equal to 0.097 divided by 2 into 0.097. So, it is coming out as 1.029 hour. So, fast falling time is 1.029 hour. Okay. Now, we need to calculate the second falling rate period time. So, for that also we need to do one, we need to get the expression for this one, but in this case you see this initial condition will be the final condition of the fast falling rate period. So, it will start from XC1 to XC2. Okay. So, that is why we can say TF2 will be like this, SS by A into integration XF to XC2, that is dx by n. We told that this is the drying rate is proportional to the square of this moisture content, means beta into x square. So, we will be putting this n is in place of n we will be putting beta x square. So, we will be writing this one SS by A, this integration XF to XC2 dx by beta into x square. So, that will be like this is equal to, we can say SS by A into 1 by beta and integration XF to XC2 x to the power minus 2 into dx. That is coming out as say SS by A into beta and into say 1 by XF minus 1 by XC2. So, that is we can say this Tf2. If we put all these values, we will be getting like this. So, Tf2 will be say 30 into 0.097 into 2 into 0.183 minus 0.097 divided by 4 into 1 by the final one is 0.01 minus x c 2 is equal to 0.097, that is in hour. So, that will be coming out to be 17.552 hours. So, the total time, therefore, we can say the total drying time T is equal to constant drying period, then first falling rate, then second falling rate. So, that is coming out to be 1.027 plus 1.029 plus 17.552 these hours, that is coming out to be 19.6 hours. So, this total drying time is 19.6 hours. So, here we see the out of these 3 drying times, say the first drying time we can say this one from x I to x c 1, then from x c 1 to x c 2, then from x c 2 to x f. So, it takes only 1.027 hour, this takes 1.029 hours, but this x c 2 to x f it took 17.552 hours. So, that is I say at the end the drying rate actually becomes very slow, due to we can say this one the less driving force, it takes more time. So, this total, whereas the total time is 19.6 hours. Okay. Now, we will be discussing about another problem that say for this continuous dryer, the drying time calculation we will be doing this one, and this is very interesting problem also. A wet solid having 25% moisture is to be dried at a rate of 1000 kg per hour to 1% moisture in a continuous counter current dryer. The drying air enters at 100 degree Celsius at a rate of 12,000 kg per hour dry basis with a humidity of 0.025 kg per kg dry air, and the dry solid leaves at 60 degree Celsius. The temperature of the wet solid entering the dryer is nearly the same as the adiabatic saturation temperature of the air leaving the dryer. That is, we can say, that is we can assume also the following data and information are available for this drying operation. The gas phase mass transfer coefficient for drying of the solid K y, that is 150 kg per meter square hour. Effective surface area, that is A star A prime is equal to 0.065 meter square per kg. Specific heat, the CPS of the solid is 0.96 kg per kg Kelvin, and critical moisture of the solid is 8%. The equilibrium moisture is negligible. All moistures are on the weight basis. We need to calculate the drying time. So, in this case, as this is a continuous counter current dryer, so definitely we have different drying zones. Here also from the problem we assume that the drying, there are 3 drying zones, that is one is the zone 1 and zone 2 and zone 3. There where zone 3 is the, we can say this one only heating of the final dried product to the final we can say this one desired temperature, and in zone 1 we can say this one the initial drying starts, and in zone 2 it is we can say this one temperature remains almost constant throughout the drying period. So, we will be solving this one systematically. Okay. So, whatever the data points we have, just we will be first jot down those like this. We can say this one, see this zone 1, that is we can say this one removal of moisture above XC, that is we can say this one removal of moisture above XC, and in zone 2, that is we can say this one removal of moisture below XC, and in zone 3 here we can say this one only heating of the solid. To exit temperature. Okay. So, these 3 zones. So, whatever the given parameters we have in the problem, we will now first jot down all these. This SS actually is given as say 1000 is the flow rate of this wet solid, with this we can see this 25% moisture content. So, it is 1 minus 0.25. So, we can say it is 750 kg, that is per hour. Then x 1 will be definitely say 25 by 75, that is will be 0.333, and x 4, where it will be x 4 or x 3 both are same when it will be exiting actually from there, because you see after that the moisture content does not change. So, that is x 3 and x 4 both are same. So, that is we can say this one, that is equal to say we can say x 3 also is equal to, so that is 0.0101 like this, and x star for this means the equilibrium moisture content, that is 0, almost 0. So, we can assume this one as 0, and gas flow rate, this drying gas flow rate is given as 12,000 kg per hour, and x c is given as 0.08 by 0.92, that is equal to 0.087, and T g 4 that is also given as say we can say 100 degrees Celsius, and y 4 that is equal to y 3 also equal to 0.0225 kg dry air, and T s 4 is equal to say 60 degrees Celsius, and C p s is equal to 0.96 kilojoule per kg Kelvin, and A prime the specific area is given as 0.65 meter square per kg dry air, and mass transfer coefficient value K y is given as 150 kg per meter square hour. Okay, so, these are the parameters given in this problem. So, we will be doing now overall moisture balance to get this y 1 value, that is first, that is unknown parameter. We will be calculating this one from this if we do the overall moisture balance across this entire dryer. So, we will be doing overall moisture balance. Like this. So, we will be taking this S s into x 1 minus x 4, here S s L s both are same is equal to G s into y 1 minus y 4. So, that is we can say this one 750 into x 1 is equal to 0.333 minus x 4 is equal to 0.0101, and G s is given as 12,000, y 1 we do not know. minus y 4 is given as 0.025. So, from here we will be getting this y 1 is equal to 0.0452 kg per kg dry air. So, now we have got this y 1, that is we can say this one this moisture content of this drying air which is leaving the dryer. So, we have got this y 1 now. Okay. Now, humid heat actually of the air C H in zone 3 will be starting here actually. So, we can say this one C H is equal to say 1.005 plus 1.88 into y 4, that is we can say 1.005 plus 1.88 into that y 4 is equal to 0.025, that is coming out as 1.052 kilojoule per kg dry air per Kelvin. Okay. So, now actually we need to take the help of this psychrometric chart to get this Tg3. So, we will be doing like this, we need to assume say for this one say let Ts3 will be assuming, let Ts3, that is we assume on one value actually we are assuming now like 40 degree Celsius. For the timing we are assuming this, let Ts3 is equal to this 40 degree, that is nothing but we can say this one adiabatic saturation temperature. So, we will be taking this one at 40 degree Celsius like this here, and then we will be taking this we can say y 3 actually is given as point y 3, that is given as 0.025, that is already given. So, 0.025, let us take this one, this line, and 0.025 this line. So, here you see we can say this one, let us take this is say 98 degree Celsius. So, that is we can say this one Tg3, that is Tg3. Let us take see this one is Tg3, whether we are our assumption is correct or not, we can get this one from the enthalpy balance also. That is for the we can say this for simplicity we have that assumed this one, we assumed that this Ts3 is equal to 40 degree, it may be another temperature also 40 degree Celsius. So, and for that we will be getting Tg3 as the 98 degree Celsius. For that, so let us take, so this we will be doing the enthalpy balance to ensure whether this Tg3 is correct or not. Let us do the enthalpy balance, very easily we can do this one. In this zone 3 we will be doing this one, that Gs into Hg4 prime minus Hg3 prime is equal to Ss into Hs4 prime minus Hs3 prime. Here you see, except this we can say this one again, we can say this one, we can convert this into in terms of H, we can say write in the form of Ch into temperature like this, or Gs into Ch into Tg4 prime minus Tg3 prime is equal to Ss into Cps into Ts4 prime minus Ts3 prime. So, here you see this Gs is equal to, we can say this 12,000 into Ch is equal to 1.052 into Tg4 is equal to is given already as 100 degree Celsius, Tg3 prime will be getting Tg3 say then it is equal to SS is given as 750, CPS is given as 0.96 and TS4 is given as 60 and TS3 is given as 40. So, now from here we can say Tg3. So, these are not prime values actually. So, Tg3 is equal to, we can say this 99.1 degree Celsius, and from the psychrometric chart we got 98 degree Celsius. So, we can say maybe both are almost similar. So, we can assume that the Tg3 is equal to say 99.1 degree Celsius. Okay. Now, in zone 3, say in zone 3 we can say this one Q3, whatever the heat flow actually is there is equal to, we can say this one Gs into Ch into Tg4 minus Tg3. So, that comes out as 12,000 into 1.052 into, this is Tg4 is equal to 100 minus Tg3 99.1. So, that is coming out as 11,361.6 kilojoule per hour. Okay. And we have this Hc is equal to Ky into Ch. So, that we have this one Ky is equal to 150 into Ch is equal to 1.052. So, that is, so 157, this is 150, that is 157.8. So, kilojoule per meter square hour Kelvin. Okay. Now, we need to get the temperature driving force. So, for that we have this one in this in the station 4 or wherever we can say this one hot drying solid is exiting and drying gas actually is entering. There we say delta T4, that is we can say is equal to say 100 minus 60. So, this is 40 degree Celsius, and here in station 3 this is we can say this on temperature driving force delta T3 is equal to say we can say this 99.1 minus 40. So, it is 59.1 degree Celsius. So, from here actually we will be getting that say LMTD delta T LMTD will be like this 59.1 minus 40 divided by ln 59.1 by 40. So, this is coming out as 48.9 degree Celsius. In this zone we can say this one temperature driving force is 49 degree Celsius, and say we know this, we have already derived this one, this T3 in the previous class we have already derived, that is in T3 this is Q by SS into A prime into HC into LMTD, that is equal to Q is equal to 11,361.5 divided by 750 into A is 0.065 into HC is given as 157.8 and LMTD is 48.9. So, that is coming out in hour, that is we got this time as 0.03 hour. So, this T3 is 0.03 hour. Now, we will be going to this zone 2. So, in zone 2 first we need to get Tg1, because see this temperature actually is not known. We need to do by some this one we can say indirect method, means say this for getting this Tg1 we need to do the overall enthalpy balance in zone 2. From there actually we will be getting like this. Before that actually we need to calculate this suppose we need to get Tg1. So, calculation of Tg1, for that we will be doing say overall enthalpy balance. We need to get this from this overall enthalpy balance. Before that, we need to get this one. We have already derived this one for enthalpy values for gases, enthalpy values for solids. This for Hg4 prime, that will be like this 1.005 plus 1.88 into say y prime, that is into 0.025 into temperature gradient, this 100 minus T0 is equal to 0 plus this y prime 0.025 into 2500, that it is coming out as 167.7 kilojoule per kg. So, that is Hg4 prime, however, it is entering here. Similarly, for getting this Hs4 prime, we have this another formula. We will be using that for Hg for gas, which is the solid actually says 4 prime, that is whatever is coming out, this we can say the drying solid, the enthalpy value will be like this Cps plus x1 into Cpl into Ts1 minus T0. By doing this one 0.96 plus 0.96 plus 0.0101 into 4.187 into 60 minus 1 0. So, it is coming out as 60.14 kilojoule per kg Kelvin. And for Hs1, so we have this Cps plus, that will be actually x4, x1 into Cpl into Ts1 minus T0. It is coming out as 94.2 kilojoule per kg Kelvin. Okay. Now, we will be doing the overall enthalpy balance across the entire dryer. So, we will be getting like this Gs into Hg4 prime minus Hg1 prime is equal to Ss into Hs4 prime minus Hs1 prime. Okay. So, we will be putting all these values to get this Hg1 prime, that is not actually available. So, we will be doing this one 12,000 into Hg4 prime. We have already got this value 167.7 minus Hg1 prime is equal to 750 into, that is we have this 60.14 minus 94.2. So, from here we will be getting this Hg1 prime, that will be getting as 169.8 kilojoule per kg. So, that is we can say this, that will be equal to just using this formula 1.005 plus 1.88 into y 1 prime, that is we can say this one 0.4 0.0452 into Tg1 minus Tg0 plus 2500 into y1 prime, that is equal to 0.0452, that is equal to, we can say this one, we will be putting this is equal to, so here you see T0 is equal to 0 degree Celsius. So, we will be putting here 0. So, now from this equation, say 169.8 is equal to 1.005 plus 1.88 into 0.0452 into Tg1 plus 2500 into 0.0452. So, from there we will be getting Tg1 is equal to, we can say 52 degree Celsius. Now, we see this gas temperature is now known, this Tg1 is known. Okay. So, what will be the Ts1? For that actually we can say this, and humidity, this y1 prime is already obtained as 0.0452. So, we will be going to this, we can say this one in psychrometric chart. So, we have this Tg1 is equal to gas temperature, we can say this one 52 degree Celsius. So, 52 degree Celsius at Tg1 and 0.0452, like this we have this one. So, from here if we follow this adiabatic saturation line, we will be getting, we can say this one temperature as like this here. Let us take, it is say Tg, this one Tg1, Ts1, that will be equal to, we can say, let us take 40 degree Celsius. So, for 52 degree Celsius Tg1 is equal to 52 degree Celsius with y1 is equal to 0.0452. We have Ts1 is equal to just 40 degree Celsius. Okay. Now, we will be getting this x2 values, that is we can say this one x2, that is nothing but this, we can say this one xc, that is we have already this one obtained as 0.087, we have this value, and from there actually we will be getting HS2 prime, that is, so that is we can say this CPS plus x2 into CPL, that is liquid water, into Ts2 minus T0, that is we can say this one will be getting as 0.96 plus x2 is equal to 0.087 into 4.187 into Ts2, that is we assume this as 40 and Ts0 is equal to 0, 40 minus 0. So, from here actually we will be getting HS2 prime is equal to 52.97 kilojoule per kg Kelvin. Okay. And similarly, this HS3 prime we will be calculating by this like CPS plus x2 into CPL into Ts3 minus T0. So, here we can say it is say CPS, that is 0.96 plus HS3 is HS3. That is will be x3 actually, that is 0.0 and x3 x4 both are same, 0.0101 into 4.187 into 40. So, that is coming out as 40 kilojoule per kg Kelvin. Now, we will be doing the moisture balance in this zone 2 in the moisture balance. So, we will be doing a moisture balance like Gs into Y 2 minus Y 3 is equal to S S into x 2 minus x 3. So, this is 12,000 into Y 2 minus 0.025, that is Y 3 we have, is equal to 750 into x 2 we have 0.087 and x 3, that is x 4, both are same 0.0101. So, from here we will be getting y 2, that is equal to, we can say 0.0298 kilojoule per kg dry air. And now we can calculate this Hg 3 prime, that is equal to, say, just by putting this value, this we will be getting 1.005 plus 1.88 into this y 3, that is 0.025 into 99 minus 0, that is y 3, that is minus 0, plus 2500 into y 3, 0.025. So, that is coming out as 166.8 kilojoule per kg Kelvin. So, now we have, and we need to get this one this Tg 2, that is not this one, we do not have this Tg 2 value, we will be calculating this one. So, we will be doing the enthalpy balance. This Gs into Hg 3 prime minus Hg 2 prime is equal to Ss into Hs 3 prime minus Hs 2 prime. That is, we can say 12,000 into Hg 3 prime, we have just calculated 166.8 minus Hg 2 prime, we do not know, is equal to 750 into Hs 3 prime is 40 minus Hs 2 prime is 52.97. From here actually we will be getting Hg 2 prime. So, that is coming out at 167.6 kilojoule per kg Kelvin. So, there actually we can say this one, this is nothing but just by using the equation in terms of this temperature, we will be getting like this, that is equal to 1 point for gas actually 1.005 plus 1.88 into y 2, that is 0.0298 into Tg 2 we do not know, Tg 2 minus T 0, that is 0 degree, plus 2500 into y 2, that is 0.0298. So, from this equation 167.6 is equal to 1.005 plus 1.88 into 0.0298 into Tg 2 minus T 0, that is 0, plus 2500 into 0.0298, we will be getting that Tg 2 is equal to say 87.5 degree Celsius. So, we have Tg2. So, whatever with the Ts actually will be, we can say this one this Ts, that is we can say Ts is equal to 40 degree Celsius, we know. Suppose this Ts1 is actually 40 degree Celsius, and now we have Tg2 is equal to 87.5 degree Celsius. So, this 87.5 degree Celsius like here. So, we can say the if we have this the Tg2 is 80, Tg2 is equal to say 87.5 degree Celsius, and Ts1 actually we have this 40 degree Celsius, and say what will be the Ys. It will be like this. So, Ys will be equal to say 0.05. Okay. So, now we need to get this T2, whatever the time for this second zone, time required to dry in the second zone. So, T2 we can say this one Gs into Xc by Ss into A prime into Ky into 1 by x4 plus Gs by Ss into Ys minus y4 into ln Xc into Ys minus y3 by x4 into Ys minus y2. Okay. Now, all the values are actually known to us. We will be getting all these values and we will be putting, then we will be getting. So, the time required in this zone 2 T2 will be 12,000 into 0.087 divided by 750 into 0.065 into 150 into 1 by 0.0101 plus 12,000 divided by 750 into 0.05 minus 0.025 into ln Xc, that is 0.087 into Ys, that is 0.05 minus y3 0.025 divided by x4, that is 0.0101 into Ys, that is 0.05 minus y2, that is 0.0298. So, this is coming out at 0.824 hour. Okay. Now, we will be calculating the time for zone 2, zone 1. So, that is for zone 1, we have this total time T1 is equal to Gs by Ss into A prime into Ky into ln Ys minus y2 by Ys minus y1. So, here Gs is equal to 12,000 by Ss means 750 into A prime is 0.065 into ky is equal to 150 into ln ys is equal to 0.05 minus 0.0298 divided by 0.05 minus 0.0452. So, it is coming out as 2.358 hour. So, this is T1. So, total time we can say this one total drying time will be total drying time is equal to we can say T1 plus T2 plus T3, that is we have this 0.03 plus 0.824 plus 2.358. So, that is total 3.21 hour. So, this total drying time is obtained as 3.21 hour. Okay. So, thank you. This we will start this next topic, that is liquid extraction, in the next class.